Okay, 6 o'clock. Let's get started. So we have this review for request. I think we'll start with the Carter's request this time. This one, can we review the clock system and memory models, etc., and accompanying question. I'll like to give you a general guideline of that part to understanding of this specific problem. Okay, before I forget, let me just start recording as well. Okay, so let's look at this generically. Let's look at these two things. Um, One is that these clock systems, and other is the memory operation. The clock system, as we understood uh, from the lecture, is that it gives a reference of the time for the operation, and then with respect to that different component in the computing system, actually it takes different action. Either it completes some request, or it basically issues some more request to the other component, and so on and so forth. So or pick up the result at a specific time point. So these are the all time references of the operation, and these are done by electronic component called clock, which is a hardware component which generates like equidistance pulse of electrical signal. Like it's an, you can imagine that as a train of 0 and 1 happening equidistance from each other in general sense. So we represent that in as a picture, as an waveform going up and down. And for us, like without getting into this complexity of rise transition time and fall transition time right now, what we can think this whole system is basically giving you this train of like squared pulses that we can think that, okay, this is my so there is a clock hardware component, okay, and as an output it's giving an output from it, and this output is continuous train of logic 0 and 1. So just pictorially we can think this is my clock. So at some point of time it is at logic 0, another point of time it is at logic 1, right? Logic 0, logic 1, logic 0, logic 1, logic 0, logic 1, and so on and so forth. And the distance between the time when the signal goes from logic 0 to logic 1 and when it goes next logic 0 to logic 1 is called a time period. So T is my time period. So definitely unit is your time unit. And in computing system, we deal with basically uh, like second, microsecond, sorry, millisecond, microsecond. And by the way, sometimes it can be written as just US, like, but it's really a micro in that context. Nanosecond, etc., picosecond. That kind of units we measure it. Usually minute hour is not a concern at the computing system, because computing system is too fast for that kind of macro unit like hours, days, etc. But it is more like a second, millisecond, microsecond kind of units there involved. Then from there we have this derived unit called frequency. Frequency is basically 1 upon T. So its unit is really is like an second inverse. That is your unit. And I think most of you went through the physics class about the frequency units and stuff like that. This is nothing but an hertz. Hertz. That's what we call the frequency unit. So, so we basically, if we know time, if we know time period, then we know the frequency. Or if we know the frequency, then we can derive the time period. It's just simple mathematical operation of reciprocating it and mark into different units, right? So then, so far any question? Okay. So basically, then there is this concept of this duty cycle coming to the picture, where it basically deal with the fact that distance, like this width versus this width, the time within a time period, how long your signal is staying at logic high and this clock signal is staying at logic low. So basically, let's say if we just denote them by logic low, okay, or maybe TL plus T high, these two time, if we sum up, we actually get T. That's very simple relation. And from there, it has one specific property called duty ratio, which is defined as this TH by T.
Professor, we can't see the Jamboard.
Oh, sorry. There you go. So what we're talking about, that this T high and T low is basically your how long it stays at high and how long it stays at low, and if you add them up, you basically end up in a time period. And duty ratio is nothing but a ratio between the T high and T low, and often it is expressed as in terms of percentage, like 100. This is your in terms of percentage, but practically it is just the ratio of TH and T low. Now you have a couple of other parameters came in, and in the problem, if one or two of them are given, then you can actually compute the other. Let's say you are given with the time period, and you are given with a duty ratio, and you have to compute the T low, then it's basically to compute the T high from this relation, and then T low from this relation. So, and if you are given from the frequency, then frequency to time period, then using the duty ratio this, then compute that. Or so you have now these problems can come with the combination of these. You need to watch out what to plug in your numbers and get your equation done. Question? Okay, now about the memory sizes and things like that.
Professor, I have a question.
Yeah.
Why do we care about duty ratio? Like, is this used somewhere? Like where it has only a specific purpose?
We don't use it in this class, but in industry, this is a very important parameter for the clock. It basically denotes how low my power consumption is, and it relates to that one.
Okay, so like if you want to make a better processor, you just basically have to cut down on duty time.
Yes, you cut down on the duty time to make it not a better processor, I'd say low power consuming processor. Usually go with the lower duty ratio for the
Okay.
clock.
So like for the clocks that are used in these processors, are they all like quartz clocks?
Or what?
Like quartz, how we have like quartz crystal in the watches? Like
Yes,
do they?
quartz are the fundamental element that gives you these frequently like repetitive electrical voltage or current, whatever you want to think of, out of these.
Okay.
And there are these complex analog circuitry around this clock generator to make a nice stable pulses of electrical signals. The couple of things involved there, like a phase lock loop or PLL circuit.
Okay.
Those are real complex circuit to kind of make an analog electrical signal coming out of the quartz element and how it can transform into a digital clean square waveform. That's a problem by itself. So
Yes.
yeah, but out of our scope.
Thank you, Professor.
All right, about the memories now, size, right? So memories, we can think it in a, I'm out of the Jamboard, so I'll start reciting from the beginning. Okay, so a memory is a information container, right? It's the memory is information container, and so if we think memory is information container, and these informations are stored in terms of bits, okay? Single bits, one bit, 0 or 1, like 0 or 1, like electrically it's stored inside it. And a group of 8 bits is called byte. And this is the unit we basically more frequently deal with, byte and its successor, like a kilobyte or megabyte or gigabyte, something like that. But it's a byte unit. Why we deal with this? Because usually we see memory as a byte addressable device. So what does it mean? Byte addressable device. Okay. So memory is a byte addressable device. That's what we see from a programming perspective, which means basically think the memory as a giant container of information, and it has separate units, a byte long units. So this is a byte, 1 byte storage, means it's storing 8 bits inside it. So it has like many such byte containers. Okay, so this is a byte container. So now our problem is easy. Like if there is the n container, 0 to n-1 as the index, if I see that, so total size is practically n byte, right? This is n byte. Uh, Now, if the problem says, well, it is a word addressable memory, what it is really saying is instead of each container containing a byte, it contains a word. It contains a word. So in that case, in terms of byte, it will be like 4 multiplied by n bytes because one word is 4 byte. That is a unit conversion. All right. So, so far so good, right? This is like an word addressable and size, etc. So in general, if we say that each container contains like like let's say B bytes. So I can say it's a double word addressable or half byte addressable, stuff like that. But in general, if it is a B byte, then we can actually have a generic formula. So it's a B into n bytes. Simple. So far, everyone agree with that one?
Professor,
Yes.
for the markers you put on the right hand side of the rectangle, those are the addresses, right? 0 and n-1.
Those are the addresses. Yes.
Are the addresses the size of the like bit?
Yeah. Now that part is coming up. Okay. So let's these are the values, right? These are the values. These are some indices we are putting in as an address of the container, right? So now the question becomes like how many bits I need how many bits are needed for 0 to n-1 address representation, right? So that's our question now. How many bits are needed? So basically, like fundamental problem is that we need to tell memory, hey, I want to access this address, like somewhere like address X. Now, how do I represent that value? Because this n is very, very large. Basically, it's thousands of addresses are there, right? So if it is thousands of addresses in terms of electronically, how we can represent it? So we decide that we'll go with representation with a binary, okay? With a binary representation of address, okay? So then it becomes a problem of the how many bits I need for expressing 0 to n-1. We all know that if it is an, let's say, n bits, and this is all unsigned values, there is nothing called negative address or anything, so these are unsigned values. So my unsigned value range is 0 to 2 to the power n-1. Sorry. To the power n-1, right? So my problem is that, like, I want to represent this much. How many bits I need? How many bits I need? Right? So usually it is the relation of n equals log base 2 of n. You take a ceiling of it. So that's the number of bits needed. Number of bits needed to represent address. So that's what you see here. Your address bus coming out of the processor has n number of bits. Question so far? So that means if you are given, so we have a couple of relation here. One is this, all right? Another is this, which practically also tell n equals 2 to the power n. Now we can, in a problem, you have to given with some of this parameter known and ask you to go for a unknown parameter. Let's say we want to, we have given you n and b, and we want you to come up with size, right? So for that case, what you do, you basically go from here, use this guy to basically compute the n, and then apply b multiplied by n, right? So that's how you do it. So other way, let's say the problem is given with, let's say it has given you the size, okay, and an address. And it asks you to go for compute the, what is the addressability of this. That means practically you need to compute B. Each container contains how much. So you apply this relation and come up with the answer. Make sense?
Yes, sir.
Any question so far? Okay, now comes to this problem that the time computation, right? Which basically tells that, let's say, this is a simple memory system operation timing diagram. And also in the problem statement, you will be given that, well, this memory is operating, let's say, completing read and write means so many clock cycles and so on and so forth. And these many, these a number of operations are there, etc., etc. How long it takes, right? How long it takes. So here, what you need to understand, one specific part is this wait time, right? This is like if you have a write operation immediately after the read operation, you need to wait for a clock cycle for the data to be consumed. Why? Because we are using the same data line, electrical physical data line, that memory is giving out the data and processor is consuming that data in the other end. Then processor obviously cannot use the same line to send the right data onto the memory at the same time point. So they need to be separate apart in the time domain. So that's why we need to separate out. Other than that, if it is a consecutive write or read, or even read after the write operation, we don't have that constraint anymore, and we can operate normally. So they won't take extra clock cycle. So usually these problems like what will be given, like number of clock cycle for the read, let's say number of clock cycle.
Hey, Professor, sorry to interrupt, but why is it okay to have a read operation right after a read operation?
Because while you are consuming this data, processor can still change the address because address line is not used at all at that point, right? So processor can actually give another read operation request onto the address of the memory and changing the address line, and it can do that. Do you see there is a conflict there?
Yeah, makes sense.
Right? So we don't have a conflict there. We can perfectly operate that one, and then that read operation result will come out in one cycle after, and processor will consume that. So same happens with the write operation as well.
Thank you.
So let's say number of read and number of clock cycle for the write. And let's say there are n, I'm using n too much. Okay, x total number of read or write operation, and let's say out of that xr equal to read operation, XW is a number of write operation, So practically this means in X equals XR plus XW, all right? So this information will be given you in one of the form, right? Either it is a mixture, like 80% mixture of read operation, and out of that, like 10% is following a write operation, and so on and so forth. So basically, okay, that's one other important thing need to be done, that how much, okay, let's say out of these, number of write immediately following read operation. Okay, so this is another quantity we have to be given with in the problem, either in terms of percentage of XW or separately, or doesn't matter, but ultimately you need to find out how many write operations are immediately following the read operation. So in this case, total number of cycles, C, let's say that's what we want to compute, total number of clock cycles. That's my target goal here. And once we can do that, then we multiply with the time period and so on and so forth, and we get the total time of the operation. So that's my target. So what is that one? That one is practically your number of read operation multiplied by number of cycles needed for the read, plus number of write operation multiplied by number of clock needed for the write, and plus now come to these extra clock cycles. Just if nothing is given, assume one extra cycle is needed, so that will be XRW, right? So this is your cycle. So time is practically C multiplied by T. T is a time period. So in this whole generic problem, you can be given with some components, right, and asked to go for this one, or asked to go for the other component. So that is the equation you need to understand and apply all through, and plug in the known values there and compute the unknown there. Does that make sense? Question?
Yeah, Professor. So why are we adding those write operations that immediately follow the read operations?
Because of this, we need to add this account this waiting time.
Oh, okay. Thank you.
All right. Now, let me see. So Carter, is that is there anything else you are looking for?
No, that described it well. I also added another question there too.
Yeah, so this one, I just turned on, like, I think Ethan came to my officer and pointed that I didn't turn on the this thing or answer for the quizzes. So I can give you this one, but just a note that I have turned on that answer. So basically,
Okay.
this question was asking for, let me see what this question was asking for. Let's do that. Okay. Just hold on, let me bring out that question first. Seventeen. Okay, this one. All right. So this one. Okay, this was the question 17 on that part. So basically what they say. So you were writing this function, my func, okay, the function does not need any argument, that's good. Return values in V0. The function also calls for another function, that func, which takes one argument in A1 and return value in the V0. To implement your function, you are using T0, T5, S1, T6, and S2. What are the registers you need to save in the function? So registers to be saved in the frame. Okay, so we all know that we need to save $FP and $RA in the frame, and then we need to save anything like $S that we are changing inside the function, and anything $A that we are changing inside the function. So this one. So practically, this should be $A1, $S1, and $S2. So these should be the answer for this one.
Professor, why do we need to not save $SP?
Because if you look at this frame creation and deletion, what we have usually like an addition of an offset, and let's say 20, for example, and then we start storing words, right? Frame pointer with respect to the stack pointer, store word array with respect to stack pointer, maybe 16, store word maybe with respect to okay, A1, 12. And 1, 2, 3, 4, 5, 20. Okay,
Would we need to make FP24 just to?
yeah.
Okay.
20, 16, S1 with respect to SP. Yeah, I think you need to check the format of that thing. I think it is more like 24, like this one, right?
Okay, so SP doesn't get saved. Its location just gets adjusted.
Exactly.
Okay,
For,
makes sense.
right? Then we are setting 12, etc., etc. Then we are setting the frame pointer to SP plus 24. And then this is my RT save code. And on the other side, on the RT restore, that part of code, what we do, we do bunch of load word. And at the end, we basically do stack pointer 24. So you see this stack pointer is implicitly saved. It's just by the operations. It is not a part of the frame itself. Your frame contains all other registers, but not the stack.
Okay, thank you.
Okay.
Professor,
Yes.
I'm still a little confused why we have to store the argument of the that func. Isn't that func also doing a store process within itself?
Right, but you are calling that function. That means you are setting up some values into it. That means you are modifying it inside your program, isn't it?
Yes, just a little confusing, I guess.
So this is takes one argument means internally. First of all, my function is not picking up any values from A1, A2, or A0, anything, right? So each scholar, myfunc scholar doesn't need to set any values there. But within the myfunc need to set some values to use the datfunc routine. So that means it's changing the value here, which is not expected by the caller of the myfunc to have a changed value. So that's why we need to set the argument register. Make sense?
Is it, yeah, is it kind of related to when we first call a function from the main, we also do a kind of like a load or like a store word or into the appropriate registers for the arguments? Is it kind of similar to that?
Yeah, yeah. So when for example, like your programming assignments that recursive LCM or those things, right? We are calling your function, but before that we are setting up the argument register properly so that you pick up the argument correctly from those $A registers. It is the same technology.
Yeah, I kind of understand better now. Thank you.
Okay.
And Professor, we don't save the temporary registers simply because of convention.
Yeah, that's a convention. Okay, so what else? Let's see. Oh, what is the difference between extern and global? So extern is defining a label without initializing them, okay? Without initializing them. And global is kind of making a label marked as global. So what does it mean? Like, say, let's see if I do an extern, some label L1, 200, right? So this is like a size of the storage. Means that assembler will set aside 200 bytes starting from the address L1. Okay, so basically your symbol table then will have this L1, some address, we don't know, and it will be marked as a global at that point, whereas this thing like L2 dot byte, you are initializing it 1, 2, let's say, and you are making dot global L2. So what does it mean? It basically having the L2 in the symbol table, some address, and this one is specifically marking this L2 as a global. So extern is implicitly making L1 as a global, and it also stores aside some specific number of bytes for starting from that address without any initialization needed. But for the global, you need an existing label which is being initialized with some values there. And then you are marking extra, like explicitly saying that, okay, this is my global label. Is that clear, Brandon? Oh, yeah, Brandon asked that question. Yeah, I'm not sure if Brandon is there today. Yeah, Brandon is there. Brandon, does that make sense?
Yeah.
Okay.
I had a question.
Sure.
So does the .global directive, does that have to come before when you declare the label, or can it be like after?
I'm not sure. It may vary from assembler to assembler if someone can look ahead. these
Okay.
levels. Yeah, but you just experiment with the mass and let us know what's the behavior there.
Professor,
Yes.
in Carter's question, so we looked at the RTE frame in functions perspective. Like, is there a perspective for like in the last line it says in the functions frame, right? Do we have a callers frame as well? Do we say what like when making a call, let's say like save the S registers before making a call to the function?
No, no, it is just by convention that we know our saved register will be touched, our argument register won't be touched.
So that's just like relying on the function that like our saved
Exactly,
will not be touched, right?
exactly, exactly.
Okay. All right. So we don't have any callers frame. That was just my
No,
original
no,
question.
no.
Okay. All right. Thank you.
Okay. The other question was this one: recursive factorial and stack and the RTE. Yeah, we can pick up the same example we did in the class. Let me see. Oh, this one, right? So here, okay. So this is a function. This is a function that that gives you the recursion, and okay. So what we are looking at is, first of all, we determine the frame size itself is 16 byte. Okay, that means your initial frame will occupy 16 byte, and rest of the 8 bytes will be freed up, like it's free to use, right? It's accessible. Now, from these functions, if there is any other function call or call to itself, and right, so this factorial can call other function or call itself like a recursive function. But in any case, next frame creation from within this factorial body, if it is calling someone else, we will start losing 4 byte access. So we can think the successive frame sizes will be increased by 4 bytes from the given frame. Because in this case, it is calling itself. So it will be 16 bytes to be stored, but will in that process will be losing 4 bytes further. So that means successive calls are 16 plus 4, 20 bytes long. So that's what we are discussing, that if in general I have a recursion depth of n, the very first byte gives me the size, okay, the 16, and then successive will be that size plus 4. That means we have to deal with n minus 1 number of frames there. So that would be the generic formula for you guys. Like maybe like if we call S the frame size as a S and depth is n, then my total peak memory is practically your size plus n minus 1 multiplied by S plus 4. Maybe you can use that formula there, and yeah, and calculate it. So for this specific example, what we determine, my n is 11, because it is basically, if it is going lower than 1, then it is my base condition. So that's why factorial of 10 will actually create 11 frame onto my stack pointer, and then we can use this formula to just do the peak memory size. Is 16 plus 10 multiplied by 20, which is equals 16 plus 10 multiplied by 20 bytes equals 260 bytes. So that's how we calculate the frame size and those things.
Professor,
Yes.
are we ever going to be asked to do frame size, calculate frame size, frames within frames? You know, if we have other function calls within a function.
Maybe.
Okay.
Professor.
Yes.
So like if you know how we have our macros defined in a different file.
Hmm?
So if we want to like define our functions in a different file, do we just like in that file make those labels as global? Is that the only thing that we need to do?
No, you don't need to make it global. You can just have it and assemble it together.
Okay. So
Yeah.
just like include the file like how we do for macros and still have the labels in different because
Right.
we're doing a jump and link statement to call the function, right?
Yes. So
Okay.
yeah, either you can do a dot include of all the source file that way, and dot global is definitely another way. You are just marking them as a global label, and then linker can associate and resolve those addresses for you and the link.
Okay, so we do not need to mark them global. If you
No, just experiment. Like I'm just answering on top of my head, but I may be wrong in there. You just make an experiment and see how it behaves.
for sure, thank you, Professor.
Okay, so this one. Is there anything else that you guys want me to discuss? No?
Professor, can we go over IO mapped IO, like over that topic?
Okay, so IO mapped IO. Okay, so that's an interesting topic. IO map IO is basically your how we are going to access the IO devices. That is the question. So here is what is done right now. Uh, Let me just come to a page where I can use. Yeah, use that. Okay, so you see, like there is a processor, and there's memory. So let me send it different memory microprocessor. So I'm talking about the physically on the board. Okay, and there are devices like keyboard, like monitor, etc., etc. Right, IO devices. Uh, the question become, and you can think this IO devices as nothing but you are fetching some data in from here, right? In general, keyboard is sending in some data. On the monitor, some data is being sent out to be displayed on itself from the microprocessor. And memory is definitely one way or other, right? So that means each of these devices need to have an address, right? Need to have an address, unique way to identify them in the electronic system. So need to have an address. So what this processor viewpoint is, is I am accessing a memory. There are addresses. Let's say 0, 1, 2, 3, then that's the 100, 101, let's say. So from processor perspective, this guy is issuing addresses and getting the data out of these conceptual memories, and your control signal, read, write, also issued into that. But the address 100 and 101 is actually on physically. These addresses are connected to the monitor and the keyboard. And rest of them are connected physically to the memory device. So you see that from processor perspective, it is simply load word, store word instruction. But if I do a store word on the 101, some information will be being displayed on the monitor side, on the display. Or if I do a load word from 100, some information will be, data will be coming in and given to the data port on the microprocessor side. So microprocessor is not even aware of there is a separate device, which is a keyboard or monitor or memory. It just thinks everything is a memory. So this is a memory mapped IO. Now, in the older days, this conception was not there. Okay, so processor actually need to know that I am issuing an address, but it is also whether it is for the IO or not. So that means same address 100, for example, can be used for addressing the memory or can be used for addressing the keyboard, depending on this setting of the IO. And that's exactly IO mapped IO.
Oh, okay, now I understand. So basically, back in the days, like they had a extra bus in the extra wire in the
It's a
bus
bit, yes,
that
it's aware, exactly.
that'll carry bit of information. If it's 0, that means there's no IO. This is not an IO address. If it's a 1, that means it's an
Yeah.
IO.
And
Okay.
then accordingly, corresponding, we had these, like there are intermediate like electronic circuitry, which basically then resolve that access, which physical device will be accessed and read from or write into. That extra electronic circuitries are there always. And that is, yeah.
All right. Thank you, Professor.
Okay, what else?
Can you go over 6B in problem set for lecture 4?
4, 6B, lecture 4. Let's see. This one, the compute 32-bit machine code. Is that the problem set you are looking for? Let me share. So is that the one you are looking for?
Let me check.
Hey, am I sharing? So Brandon, this is the problem you're looking for.
Yeah.
Okay, let's look at the solution. So anything specific bothering you in that problem solution?
I think I had a problem with one of them.
Okay.
Then I asked you a while ago, and I think you forgot to follow up.
Let's see.
Professor, for questions like this, are we going to have to memorize the opcodes for each of?
Remember, you have that mixed wheel sheet.
Okay.
There's nothing to memorize. Don't try to memorize anything. Just understand the whole subject.
D, 4D.
For B,
D.
D, okay. Yeah, let me see. What was that mission code again? Let me just separate them out. SRL, okay. SRL, shift right logical. Okay. So for this one, why don't I just open up the worksheet? So SRL is shift right logical, which is RD equals RT and the shift amount, right? So that means this is your RD, this is your RT, and this is your shift amount. So, and your opcode is given for this guy is 0, and this is like 2 hex, 0 to hex, 0 to hex. Remember, this is 0 to hex, which means your opcode is all 6-bit 0, and function code is 00010. Okay. And then your shift amount is 13, which you translate into the your this. Let me just go. Which is basically you translate it into this your binary conversion. RD is your 21. So is that correct? This 16 4 1. Yeah, this is 21. RT is your 19. So this is like 16 and 3. Yeah, 19. RS in this case, since RS doesn't participate in this operation, you basically put 0 there. And then we put together this according to this format. Right? This is R-type instruction. So we put together the binary code and make it in hex, right? By grouping them 4. Is that
So you wouldn't have to put 0 for the RS. You just leave it out and you'd know it's 0.
this one? RS
Yeah.
is RS is 0 because your this guy is telling that SRL is a function of like destination register. It involves the RT as one of the source registers. So RS field is not used. Nothing used is you put 0 there. Make sense, Brandon?
Yeah.
Okay. What else? Or we can actually stop here tonight if you don't have any question. And you can definitely contact me over email before the exams, the exam days, and I'll try my best to answer your question. Or in the discussion, put them in the discussion so that others can answer too, if they are aware of that. And then good luck for your exam.
Thank you, Professor.